Good afternoon, everybody. My name is Spiros Patsurakos, and on behalf of the Governing Council of Hel.A.S, I would like to welcome you to the second monthly Colloquium of Hel.A.S. The concept of the Hel.A.S monthly colloquia indeed originates from Tassos Anastasiadis, and then it was Vasilis Harmandaris who took the first step into its implementation, followed by Nektarios Vlachakis, Kostas Tassis, Kostas Vourlidas, and myself. Tonight, we are extremely happy and honored to have among us Dr. Angelos Vourlidas of Johns Hopkins University's Applied Physics Lab. Angelos is a graduate of the Physics Department of Aristotle University of Thessaloniki and obtained his PhD from New Mexico Tech. After spending almost 17 years at Naval Research Lab at various positions, including that of section head, in 2014, he joined Johns Hopkins University Applied Physics Lab, where he is the solar physics section supervisor. Angelos' research is on solar and heliospheric physics, space weather, and space instrumentation. He essentially studies the entire space spanning the chromosphere to the inner heliosphere, and he is a world leader in the study of solar eruptions. Angelos is heavily involved in space mission, being the project scientist of the coronagraphs and heliospheric imagers on board virtually all space missions, all the way back from middle 90s and SOHO, going next to stereo, and more recently with Parker Solar Probe and Solar Orbiter. He is also a rocket scientist, being the PI and project scientist of the Volt and Veris suborbital payloads. Angelos will speak to us about a historic, by all accounts, space mission called Parker Solar Probe, our mankind's first journey into the stellar atmosphere. Angele, please, the stage is yours.
So, Spiro, and thank you everyone for joining today, this evening. I'll try to not work you too much in now with the lockdown, to give you something to think about, because the Parker Solar Probe is indeed quite an audacious mission, and has very many unique characteristics, both technological and scientific. And so today I will try to give you a grand tour of both aspects of this particular mission, and hope to whet the appetite, at least of the solar and heliospheric interested members of the audience for more. So I'll start with the before I start, of course, if you have any questions, you can put them in the chat, and then we can go through them in order, or raise your hand after I finish. So, you that you're involved in solar physics, you can know that solar physics have several long-standing mysteries, which of course are not only particular to the solar case, but they extend to stellar physics, and which has become even more pertinent now with the discovery of exoplanets and the natural questions that have arisen about habitability of those worlds. The only way to assess, to try to answer those questions for objects that are so far away, is of course to study the sun and try to extrapolate from here. So one of the big issues is, why the solar atmosphere is so much hotter than the surface. And here's a variety of images taken from one of our spacecraft, Solar Dynamics Observatory, spanning and the HMI, the two instruments, HMI and AIA, spanning the surface, magnetic field, all the way up to the hot corona. And as you can see, the temperature starts from 5,000 Kelvin or so, and rises up to several million, particularly for flares. Now, this question has implications, particularly in terms of the solar wind generation, which is our next question, is how the solar wind or how stars generate winds, how they accelerate, and what are the physical processes behind this energy exchange between the heat in the corona and in the planetary space. Now, the solar wind, of course, is a lot more interest to us since it buffets the Earth, and thanks to the magnetosphere, we are protected by its detrimental effects most of the time. But of course, when we have intense solar activity, that can create disruptions both for space assets and to Earth through the generation of ground-induced currents. And so the solar wind generation, in particular acceleration, is of key interest, not only for physics, but also of societal. And another societal aspect, which again is a very key objective of the probe, are the solar energetic particles. And that is becoming more and more of concern as we contemplating sending astronauts beyond the protective cocoon of the magnetosphere out towards the moon and of course eventually to Mars. These are the the main threats that they will be facing, particularly because solar energetic particles are so hard to predict and they move at relativistic speeds almost. So it's very hard to protect against. So probe is going after those three questions, but the question the question is, why do we need to send a probe close to the sun? Well, the issue is that we don't really know much about how the solar wind generates. Here is just a regular sequence of images from our coronagraphs on the stereo mission with 15-minute cadence. So it's all you see here several days or about a month, I think, of what is going on in the sun. You know, it's very different than what we see in broad daylight with naked eye, right? It's the corona that we see here in the visible light is quite active with both transient and explosive events superimposed on a general field of outflowing material. But because this emission, of course, it is optically thin, we're just seeing here the reflection of the photospheric light by the electrons in the corona. There's a lot of superposition, so it's very difficult to just by analyzing these images to figure out whether what is going on in the solar wind. How much of that activity that we see, it's superposition, some of that is generated, say, behind the occulter, the black disk that I have in the image, and how much comes from the surface, you know, the white circle at the center. So remote sensing was really remote imaging was really our only way to assess the properties of the solar wind and the corona in general. And it was quite a question even from the get-go that of the NASA's creation. Back in '58, the Simpson Committee were report on several ambitious programs for the newly created NASA, the agency. It had proposed several probes. One was to go out of the ecliptic, which is the Ulysses mission. Another one was to go outside of the heliosphere, which is the interstellar probe, and one was actually to go into the sun to study the atmosphere from in situ. And so the third one, I mean, both of course, all of them were very technologically challenging, but the probe in particular had to face a lot of engineering challenges, mostly because of the heat. You know, as we approach the sun, the heat increases with the square of the distance, and so the new materials had to be invented, and of course a way to communicate from so far close to from inside the solar corona. So it took, as you can see here, decades for this to happen. And so first I would like to go over the sort of the technical aspects of it before I go into the science. Now, why so both amazing and technologically difficult to go too close to the sun? Well, here is the sunset from Patras. It's a picture I found on the internet. And here's the sunset that if you were on top of the probe at the closest approach. So the sun is quite much larger, and the heat is that the probe is going to witness is quite intense. It actually rises to about 1400 degrees Celsius at the front of the spacecraft. So to do that, we need a shield. We need to protect the instruments behind it. And here to the left is a picture of the heat shield being prepared at APL. As you notice, actually, that this is quite a thin shield, only about 12 centimeters thick, made out of carbon-carbon composite in layers, kind of like an onion. To create these gaps between the layers, prevent the heat from efficiently transmitting across. Plus, there is a proprietary white paint in front of the heat shield that rejects 99.999% I think of the incoming radiation. The end result is that while as I said, the temperature in the front of the heat shield is 1400 degrees C, at the back end, where the engineer is actually in this picture, will be room temperature, 20 degrees, nominally 25 degrees. That translates to about a loss of 3 million watts over that space of 12 centimeters, which is quite an accomplishment. Yet that was not enough. Here on the picture in the middle, you see that the engineer is installing a set of coolers filled with water, which so they look to have about the same size as the spacecraft. See the coolers and the spacecraft, which is as you can see about the size of a refrigerator. And the reason for those coolers is to cool the solar arrays. Even though we are close to the sun and we have a lot of power to charge the batteries, well, the heat is so intense, and we can only we only need about a thickness of 5 centimeters, I think, of a solar array to keep the batteries charged. Yet even that small area, it gets extremely hot. So it requires all of this cooling system to allow the spacecraft to operate. Now, there are many other firsts in this mission. It is the most energetic mission we have ever launched at this parameter C3 of 154 kilometers square per second square. So it's took the record over from New Horizons. The reason for that is that the mission design required the spacecraft to go directly towards Venus for its Venus gravity assist. So that means that we needed a lot of energy to overcome the speed of the Earth, so that we can basically break the spacecraft speed down, so we can fall into the sun. The mission has 24 orbits, so it's quite extends over seven years for the nominal mission. So we have time to basically step progressively closer and closer to the sun by doing Venus gravity assists at certain times, about 3 times after every 3 orbits or so. That allows us to basically monitor the environment, because we don't know anything really about how dangerous the environment is so close to the sun in terms of dust particles, energetic particles, whether the heat models that we have for the spacecraft follow our predictions and so forth. And of course, the mission will achieve both the closest approach to a star at only less than 7 million kilometers. And given the Kepler's law, it will also be the fastest man-made object. It is the fastest man-made object. I think we went over 480,000 kilometers per hour in our last perihelion. But as you can see here, it will reach 720,000 at the closest approach, which is quite challenging, particularly for us that we need to analyze the data from such a fast-moving probe. The mission, nominally, as I said, has a 7-year duration, but of course, nothing prevents it from going longer, since we don't have any indications of any spacecraft serious spacecraft malfunctions or anything deviating from our modeling so far. Of course, the closest approach will be the closest approach. We cannot do another gravity assist, as far as I know, to go even closer. So we will keep orbiting at 7 million kilometers for as long as the spacecraft lasts. So this is a visual tour of the mission. This is more for you that you look at the slides later. We launched in the summer of 18. We have several perihelion. The first one was already at 35 solar radii. It was a record. And we usually have 2 or 3 perihelia at the same distance so that we can create a baseline both for the analysis of the science data and for trending for the spacecraft, understanding the spacecraft operations. And so we are now just completed our 6th perihelion at the end of September. And I have some data to show you if we have time later. And of course, we keep going for one more orbit in January at the same distance. And then we're going to get closer. Now, this particular mission design is not what we usually have in the missions that I'm involved with. We're at the 1 AU, either at the L1 point or in orbit around at the same orbit as the Earth. And so we have basically a constant, if you like, viewing distance to the sun or to the corona or whatever else we study. Here, though, we're going closer. And by going closer, we have a unique opportunity to actually rotate at the same rate as the sun as we approach, so that we co-rotate, and then we move faster than the sun when we're at the perihelion, which means that we during approach and when we return, we spend about a day at basically the same angular distance of the sun, but we're moving radially very quickly. So basically we're doing a scan in radius over a particular point on the sun. Now the point, of course, is this, I'm talking about several tenths of thousands of kilometers, you know, about a super granular thing, 30,000 kilometers or so. When we are at super rotation, as it was the case in the last month, we moved almost 90 degrees across the sun within a matter of a day. So that means that we can scan many different structures in the solar wind at almost from the same radial distance. So this combination, you can see, is of course new, and we're still learning how to analyze the data. But you can imagine that, you know, it gives us a completely different tool capability to study this stellar atmosphere. Now, the spacecraft, like as I said, is quite small. It is like a refrigerator because of these engineering issues with cooling and necessity for cooling, and a lot of other protection aspects. I don't need to get into at this point. The spacecraft carries only 4 payloads. 3 of them are in situ, which makes sense because the whole point of probe is to go and measure the atmosphere in situ. So we have a payload that measures the magnetic field. Here are the fields that measures magnetic field and electric field, so you can get the distributions, the velocity distributions for electrons. We have the sweep that studies the ambient solar wind, the plasma, protons, helium, and in electrons at thermal energies. And then we have the energetic particle package that then looks at the energetic particles, the energies above a few keV up to, I think, 100 MeV or so. And then, of course, finally, LIST But last but not least is Whisper is our the instrument I was involved with as a project scientist, and we are situated in the forward-facing part of the spacecraft on the RAM side, as we say, so that then we can take pictures, image basically the coronal region that we eventually gonna measure with in situ instruments. And so there is this tight integration between the remote imaging, the context, with the in situ measurements. Now I can go through a tour of some of the big results from the mission, and then we can talk more. So first of all, I'll start with our instrument. This is the view from our two telescopes. We have two telescopes similar to the stereo heliospheric images, if you're familiar with that mission, that span from about 13.5 degrees from the sun all the way to 105, which gives us a very broad enough field of view when we're close to the sun to monitor propagating structures across. And as you can see here, of course, we can see the Milky Way and a lot of planets that sometimes are a nuisance more than help. Now, the main question, I guess, or that people had when we started the mission is how the coronal mass ejections look from nearby. And so here is a movie from the combination of our instruments in projection. It's going to start playing, I guess. But you can see here on the right hand side snapshots of CME structures in two different perihelion. So E stands for encounter, is our closest approach, and the number of the perihelion. So E2 was in April of 2019. You can see here a snapshot of CME. Now I have removed a previous image for that. These are running differences, so we can remove a lot of the background. And then what you can see, of course, is you can see a bright, relatively bright front, an area that is a void behind it, and what we usually call a core. And this is the expected projection morphology for a magnetic flux rope, which is a slinky or an inductor, if you like, out in space. And as you can see, that other CMEs, and actually I tell you, most of the CMEs that we've seen have the similar structure. Here is again that core that in this case you can see that in the very center of it, it's empty, it's dark. There's not enough plasma to be recorded by our instrument. And this is quite intriguing. We haven't before detected such clear evidence of voids in the center of the flux rope, but that's what a lot of the theories predict. And then also what you can see here from that's interesting from a physical point of view, you see a brightening at this case one end of the flux rope. That suggests that this magnetic is so magnetic in nature that it's trying to expand and is compressing the plasma that is entrained in the coronal mass ejection. So there is obviously some information here about the interplay in the internal force of magnetic field, the interplay between plasma pressure and the magnetic pressure, which once we are able to analyze this in detail, we might be able to get a better understanding of how the magnetic field inside this coronal mass ejections evolves, which will then have important implications on how geo-effective, how important for space weather are these events. This, of course, are slow CMEs. We are in the solar minimum, yet all of them, and here in E4, I have another CME, which is basically that slinky, if you like, seen from underneath. You see in the underbelly of the slinky, and that's why you see this sort of V-shaped features spread out in radial distance. I know maybe if you're not familiar with these images, it might not be all this very obvious to you, but trust me, this is all very consistent with what one would expect from a textbook flux rope. So this is one of the findings that we have so far. Pretty much all the CMEs that we've seen, there are not that many, there are maybe 10, 15 events, have this particular feature. So that might be because we're so close to them compared to 1 AU where we have a lot of other intervening structures. More importantly, though, is what we actually measure in situ. And so the first result, which is has become in quite the fashion in within the PSP science teams, are these so-called switchbacks. And what are those switchbacks? Well, here is a magnetic field profile from our very first perihelion, showing what has been explored up to that point. And this is what was measured from fields. And what you can see, of course, is that, first of all, the magnetic field, these are the dotted lines based on the 1/r² modeling of the magnetic field, seems to follow generally what we expect. The magnetic field drops as 1/r². However, it's this fine scale modulation that was a bit unexpected, particularly because the field seems to go from negative to positive values very quickly. And this is interpreted as basically having the magnetic field lines as they come out of the star. They make a bend, like a Z structure that propagates outward with the solar wind. It's like when you have a cord and you induce an oscillation in it that goes out in space. Now, these doesn't seem to be waves. The initial studies suggest that these actually are pressure balanced structures, maybe. Or the question, of course, is where they're generated. Are they generated in the inside the corona, or basically very close to the surface, and they propagate outwards, or they form as this picture in the upper right shows as part of the natural evolution of the field once it sort of escapes, if you like, the closed field regions of the sun. This will have has implications for theories of how the solar wind is powered. This could be results of magnetic reconnection lowdown that we see these effects farther out, which may be a way to energize the magnetic the solar wind. Or it could be maybe shear, velocity shears, although this is thought that is not probably the case anymore. Or I don't know what else. This is all intense, and you should probably keep an eye on the next special issue, I think, of ANA with first results, because there will be several papers on this. But the question is that these are now compressible fluctuations, and compressible, this is the density in blue, which means that if they are compressible and they make density enhancements, then that means that we can see them with our naked eye, if you like, with our imager. So we're looking for them, and I'll come back to that. Now, the other surprising fact was that we saw the solar wind to be actually co-rotating farther out than we were expecting. Generally speaking, our models assume that as the magnetic field kind of expands outwards from the sun, what is close to the sun, it co-rotates for a certain period until it crosses the alphanic surface, which is where basically the wind becomes super alphanic, which is the fastest characteristic speed of the medium. Therefore, no information really can go back towards the sun. Therefore, the field is disconnected from its origins. It doesn't know what the sun is doing anymore, and therefore it should propagate. There should be no co-rotation as you go out, and that really is the result of of the Parkley spiral, as you can see here in this sketch, that we measure at Earth. We measure this sort of angle of 45 degrees on average for the field. So the question was always, where exactly is this alphanic surface? Because that will tell us a lot about the physical properties of the solar wind acceleration region, which is taken to be within that radius. So many of the models say that this surface is, in general, between 10 and 20 degrees. Of course, it varies as the magnetic field in the sun increases during solar maximum and wanes during solar minimum. Of course, if we have CMEs and other magnetic field reconfigurations, it will change. So it's not going to be a smooth surface for sure. However, nobody really expected to see such a significant transverse speeds, meaning that the field is basically still feeling the sun, still co-rotating, even at, as you can see here, at 34, 5 or 40 solar radii away. The speeds, we were expecting things closer to blue, to the blue curve. And then we are getting, these are two perihelia, but we're getting the same picture, very high speeds as we approach to the sun. I have not yet seen, though, new numbers to see if we're actually getting towards this rigid co-rotation curve. So that was a surprise. And this tells you, for you that are more familiar for stellar, from a stellar perspective, that this is, of course, the rigid rotation assumption that the magnetic field basically rotates with the sun. And this is sort of the situation that we have now, that the magnetic field lines, of course, angle as they go out from the sun, creating this particle spiral. And so the question is where that interface between rigid and non-rigid rotation takes place. That also has implications for solar particle propagation, the CME propagation, a lot of things down the line that we hopefully will learn. And speaking of energetic particles, it's another subject close to my interest. We had, again, unusual findings. Let me first try to orient you of how we present this data. Here on the right is the orbit. Is the orbit, the full orbit from Venus to perihelion and back. And on it is superimposed the measurements between the epi-high, which is the high energy particle sensor, and the low energy particle sensor as a function of the orbit. And when the color tries to give you an indication of the energy and population numbers, and of course the height is the energy, a sense of the energy. So you can see that this is the first perihelion, 2018. We were still at minimum, and we still are at minimum, but we were still approaching the minimum. And what you can see right away is that we did see several events, both far out from the sun and closer in. We had a relatively big event, and I'm gonna clarify this all the way through. And this picture continues to happen in every perihelion. We see particle events every time we go through. Now the question is, do we see those at 1 AU? And the answer is no. These are they look big here, but they are very weak in terms of energy. Here on the left, you can see it's about 100 keV type of particles. So we will never see those from 1 AU, but we do see them at 0.1 AU. And what does that tell you? I think right away it tells you that the sun is capable of accelerating particles all the time, even at minimum. Small energies, sure, but these particles are accelerated by some process that is not a CME that we can see, or some other, or a flare. And so that also tells us that every time we see maybe a brightening or some sort of a motion in the sun, maybe we should expect energetic particles to diffuse out in the near sun space, which would then act as seed particles in case if a bigger event comes out and encounters those particles in its front, and then they can reaccelerate them to higher energies than otherwise would be the case. So this is one quite important implication, I think, for space weather and for understanding particle, the history of the particle measurements we have for the last 30, 40 years. And here's an example, and one, in a sense, a worrisome example from a space weather perspective. we did see in our first perihelion the evidence for very high energies in iron and other heavy ions. Of course, none of this was detected at 1 AU. It was only detected at the probe when it was at 35 solar radii from the sun. And type 3 bursts, so type 3 bursts and all the sort of the usual ingredients for a major SCP event only was weak. But then when you look at the sun, the only thing I would find was a surge. A surge is just an ejection of heavy material, basically cold material from the chromosphere into the corona, without necessarily creating a CME. It's usually small events. But in this case, as you can see, this event created a wave, and so this wave. We see these waves when we see other energetic particles, when larger energetic events. So apparently, even this very small, in this case, very small wave, we would not really have paid attention to this if it was not for this event from probe. They are capable of accelerating particles, and particles at heavy ions, which means that if we had a big CME behind this event, you could have found a already made population of quite heavy ions to accelerate and possibly create a geoeffective event. Okay, so now I'm going to switch to a few things that are not solar per se, but we can actually have interesting observations from the probe. And one is the dust. The question about the dust-free zone around the sun, which has been postulated since the late 20s. It is expected that the dust close to the sun will be, vaporized due to the solar radiation and eventually, be expelled from the system. And the only reason that we still have dust around is because it's replenished by comets and so forth. But we have never been able to see that dust depletion because of the intervening dust between Earth and the sun. And in this case, of course, is one of the first things we looked for with our instruments. Here is a movie of the F corona, the dust corona from our instrument, from our inner telescope. As you can see here, as we approach in and out, it changes in volume. And when we try to trace the brightness all the way from 1 AU to our observations, we now, for the first time, seeing the deviation from the model. We do see that the extrapolation of, say, the 1 AU dust towards the sun, which does not assume a dust-free zone, is actually wrong, and this seems to start from around here 13 or 14 solar radii, that there is some sort of depletion. So we expect that as we go closer and closer in, and our inner field of view comes closer to the sun, we'll be able to extend this curve and indeed see how far will the depletion get. On another aspect, we were able to find the dust ring around Venus. This is also really because we have to remove the F corona, so we have to create background models to subtract from our images, and this is the result. We actually see a persistent ring around the orbit of Venus. Again, this has been postulated but never seen so clearly. And so now our next target is Earth, to see if we can actually extract the same thing for the Earth. That's up in the future. And of course, comets and asteroids. Some of you may have seen a couple of weeks ago, we had a press release for our first sun grazer comet that was detected by WISPR. This is the Neowise, where we can see both the ion tail and the dust tail. It was one of the better pictures. And we also now see dust trails of comets. Here, I know it's a bit difficult to see, but you see here a line that it changes shape. You can see here it changes curvature. This is the dust trail of Phaeton, which again was not expected to be seen, but obviously we see it, and I think as we go closer, we have a different our aspect angle changes, and we can see it clear or more clearly. But here is the proof that we indeed see dust from Phaeton that can be used to analyze the object, particularly with a mission that is about to go investigate it. I think it's a great motivation if they needed one, and the indication of the synergy that one can have between completely disparate missions, planetary versus heliospheric. So I'll gonna stop now, and I'm not gonna go into this. We can discuss if you want. The only thing I want to stop with is the advertisement for our first meeting that was postponed. It was supposed to happen in March this year, but it was postponed due to COVID, and we plan to have it hopefully in person somewhat at the APL. And so keep an eye out for the abstracts for this. So thank you for your attention. I'm ready for your questions.
Thank you very much, Angele. So, yes, whoever wants to raise your hand.
They have in the chat, there are some questions, I think.
Yes. About switchbacks and CP seed particles.
Yeah, so to answer Manolis' question is in the chat, in regards to switchbacks, how do they relate to the magnetic islands that Zhang et al. And Khabarova et al. Have published over time? It could be. They don't seem to be, though, flux robes. You would expect that the magnetic island in 3D is a flux robe. And at the moment, there hasn't been any indication that these are indeed flux robes. So the jury's out. We expect to see more. I guess we need to collect more data.
Sure, it's an open subject, I think, Angele, but as far as I can remember and I understand, these are kind of blobby closed structures in the solar wind, pretty much like pebbles on the riverbank or something. So they are kind of assigning these to in situ structures happening in the solar wind. And I was wondering whether you have any indications in this respect on the geometry, or whether these are kind of blobs or closed structures in the switchbacks that you see with PSP.
Yeah, so at the moment is the cartoon that I showed, that they look like bends in the magnetic field. So they look more like alphanic type perturbations than blobs themselves. But in terms of blobs, do I have any of that? So here is one from E6 that is not to be photographed, apparently. But here is, so these are switchbacks here. I hope you can see my pointer, right?
Yes, I can.
Here in the center. So you see that these switchbacks, these are called switchbacks, are superimposed on somewhat larger velocity perturbations and density and magnetic field perturbations, and within density. So we think that there are blobs, maybe, that somehow contain or follow these structures, or somehow modulate them. So there might be, that's where the blobbiness might come in.
Mm-hmm.
But the blobs themselves, I guess the ones that have analyzed, they don't look like flux ropes, so they cannot be magnetic islands. But still, beginning.
Yeah, it's pretty easy. It's quite open. It's wide open, I would think. Yeah, thanks.
And I see another question from Christina about the pre-existence of seed particles during an SCP event could be particularly relevant to the case of GLE. Yes. Are there any relative indications in the recent PSB data? So far we so far this is from the 6th perihelion. We had some big events. You see one on the 26th of October. That was also, there was also a solar orbiter event. I don't think it's from the same event though, so be careful. But this is our first sort of shocked accelerated type event, and we had another one in September 30th, which is not clear yet if it was a CME related or not. But so far we haven't gotten enough big events to know that, oh yeah, we saw some small events and then there's a big one and comes and creates this high energy population. So we can then attribute what I was saying before, this low level activity and acceleration as the seed activity for the larger one. It will happen. Stay tuned. The activity is picking up.
Angelos, thank you very much for the answer. I'm Christina. I work in the Italian Space Agency. I was wondering, what is the higher energy that you can detect with the payload of Parker Solar Probe in particles?
Yeah, it's not 500 MeV, but it is close to 300, if I remember right. MeV.
Okay, thank you.
Yeah, one of the expectations is that we're not going to see such high velocity, so high energies that close to the sun. But of course, you know what's going to happen.
Yeah, but it can, yes, it can be a good feedback for a very long debated question on the source origin of SCPs, and in particular of very energetic SCPs, like the ones that cause GLEs. Thanks.
Sure. And I see a question from Canaris. What is the configuration of the magnetic field in open closed field lines? Can you tell me exactly what you mean with that, Canary?
Yes, I was wondering, just a moment to, I was wondering about the closed magnetic field lines in streamers and open field lines around the equator. And related to that is my second question about the quotation radius. You quoted a value of about 10 solar radii, which I think it's too small. I mean, for a theoretician to understand. Usually, we take something larger, 20, 30 solar radii. So I was a little bit surprised. I mean, is it really 10?
No, I don't know. We'll see. But there was that was one particular model that they were using, that they use in the sweep team to do their studies. That's the reason for the 10. We don't really expect to. We don't really expect this to be a constant number anyway.
It changes a lot, of course.
It will change a lot, but you might expect that during the solar maximum it gets low, that low.
But we're now at solar minimum,
Now the thing that, of course, that we have seen from LASCO for 25 years is that we for example, with LASCO, we never really saw the Parker spiral. And we were expecting that, particularly for very bright streamers, that we were going all the way to the field of view of LASCO C3, which is about 50 solar radii, depending how you project the streamer, that we should have started seeing that deflection, and we never saw it. And the results from sweep actually support that the corrotation stays strong for quite a while. So I'm waiting for the next iteration of this paper, basically, to see what the new numbers are. And I should say that the data is public, right? I have to tell you, here it is, that it gets public 90 days after its perihelion. So in 6 days, the data should be released. Our data for sure, but I assume the in situ data. Most of it should be released, and you can get it from the main Parker Solar Probe page that will take you to. You can also, there is an interface there. You can actually do a quick look of what data you're interested in. So please go for it, for sure.
Okay, thank you. Thank you again for this nice talk. Thank you.
Thank you. The radial distribution. So Lucas asks, what is the radial distribution of switchbacks? I don't know. I mean, I don't think we have put that together yet, because usually the analysis is done, in for a particular perihelion, And I have not really, I had another thing. Let me see if I can, I don't think I have it. Let me see if I can visualize this. What is happening? Let me see. So you see the switchbacks tend to be inside the heliospheric plasma sheet, not here in the what is the open field. They vary a lot, but they seem to be happening mostly, and they seem to come in bundles. I have another figure here. I know it's a bit hard to see. Yeah, here's a paper from Alexis that really tried to trace from 1AU. These are structures, blobs seen in the coronagraph and the heliospheric images field of view, two areas where there were a lot of switchbacks. And at the moment, the only thing we know is that, of course, that, you know, when you see these big streamer blobs or something like that, they do have a lot more switchbacks in them. But now, how that changes radially, I don't think we have collected all the data to say if we can convince ourselves, I mean the whisper people, the imaging people, convince ourselves that we see switchbacks, then we could trace them in radius. But with in situ, it would have to be more of a statistical analysis. And I tell you, you know, it's hard. Here is, I was going to talk about Alexander's paper, but I wanted to show you how difficult it is to track things. Here is the 6 perihelion zoom of the perihelion of 3 days in a running difference movie. So you can clearly see that we are approaching into a streamer. The streamer opens, and we see continual outflow in bursts. But to make sense of it, I mean, it's hard. And occasionally you see some black lines crossing very quickly. These are structures that went over us, and those are flux ropes. I mean, there were only 2. But the rest this is the challenge that we're facing, and we're trying to work with Alexandros Spiros and the other people, is to create maps, accurate maps of tracking those features in height, and then we see which ones are switchbacks and which are not. Good luck.
Are they connected to the solar energetic to energetic particles at all, or they have no relation to accelerated to particles?
No, not in so far. No, there hasn't been a one-to-one, say, event in ISIS with a switchback. We do see particles though in CIRs, which are, I mean, not CIRs, streamer interface interaction region. So early baby CIRs, we already see particle acceleration there. So that has to come from some of the interplay between, you know, due to compression. In this one's not yet.
Thank you very much. Very nice talk. Thank you.
Thank you. Yeah, I see from Dimitra asking about if I would like to comment on dust distribution. For example, ionized versus neutral dust particle population, and whether you expect a strong latitude dependence of the distribution in any planetary space. Well, yeah, that's a great question. This is the dust was not allowed to be our nominal objective. It had to be only a goal. And so we are committed, you know, we spend a lot of time analyzing dust from the images because it's really the only way to get that latitudinal distribution. So far, since, I mean, we're in the ecliptic, so we're not seeing anything different than what we see from 1AU. What we expect to get a handle on that latitudinal is with solar orbiter, where we have a semi-similar instrument, and then we start getting we'll eventually start getting 10 to 20 degrees above the ecliptic, and then we will see if the models we derive from this will match the view from 15. So that's one. So I cannot tell you anything about latitudinal, but we do expect to see some latitudinal effect. The other one, ionized versus neutral dust. we have not seen an event yet. We have not seen a CME sweeping out dust or a bright enough comet. I mean, except for the comet, you know, we see that part, but we haven't really seen yet, or evidence that this amorphous thing that you see here in the picture is actually modulated by the K corona. So not yet. I don't think we understand the instrument to that level, which has to be below 1%. I think for the photometry for us to be able to tell that. But keep an eye on that. That's definitely a big. It's going to be a big focus coming forward. From Yorgo Juliara, from your point of view, when the instrument will reach on the last perihelion, will it be a position to observe alpha waves on corona? We can observe the alpha waves not observe them, but measure them with the in situ instruments, and we see a lot of those, a lot of alphanicity, and this is measured. Is one of the sort of standard products that the fields and the sweep instrument are deriving, or they're trying to derive, because they try to course correlate their velocity with the magnetic field measurements to map the spectrum of the waves. So we see them, and maybe we should see bigger ones. You know, maybe we should see this ion cyclotron waves generated as we come close. Yeah, we see those. So I think that's all I see in the chat. If anybody has anything else, I'm glad to answer live.
No. So anyway, Angelos is always available for a chat via email, etc. He has been tremendous for our community in Greece, helping out everybody in all possible means, advice, etc. So let's thank again Angelos for giving us this very exciting talk, and see you in 1 month with the next colloquium of Hel.A.S. Take care, everybody.
Thank you, everyone. Thank you. Have a good evening.
Bye.
Bye.